Hi, ಎಲ್ರಿಗೂ ನಮಸ್ಕಾರ. Welcome to my YouTube channel. I am Santosh Kumar. Today we are going to discuss on data center cooling solution. So a new technology which is involving energy optimization of HVAC pertaining to data center and lab. So today we are going to discuss on precision air conditioning unit, indoor cooling system, and liquid immerse cooling. Little bit more we discuss on a precision conditioning system because most of our data center and lab infrastructure at present it is enriched with precision air conditioning system HVAC setup. So a little bit more on PAC units. So let us quickly run today what and all things we are going to see. So as discussed, a precision air conditioning system. Currently, it is there are three types of PAC units which is available at market. One is PAC with the chilled water, and second is PAC with the DX direct expansion units, and third is PAC with both chilled water and DX that we called as a dual fueled PAC units. So usually the PAC unit supported lab and infrastructure, it is uncontainment room cooling, so there is no hot or cold asile, and many of our lab or data center infrastructures. Okay, so in that situation, so the rack density up to can uncontained room cooling, it can support up to 8 to 12 kilowatt rack density per rack. Up to 8 to 12 kilowatt of rack can be loaded. So with the same HVAC PAC setup with the hot or cold assignment, so the rack density can be increased up to 0 to 22 kilowatt. And a little bit we discuss on PAC with the free cooling setup. And in this free cooling also there are two methods. One is direct free cooling where 100% fresh air pumped to lab and data center, and indirect cooling, so where only adding additional condensation coil we can uh, what reduce energy, and so that also we are going to discuss today. And next is on indoor cooling, so where the indoor cooling IRC units are located uh, parallelly to the racks. So with this with hot or cold containment, so IRC with cold aisle containment and IRC with hot aisle containment. So with this IRC, it is placed very near to rack, the parallel to rack. So obviously the airflow requirement is pretty much less compared to PHC units, and this obviously reduce the fan capacity also to meet the required CFM level. So in this with this IRC cooling, the rack density we can up to 40 kilowatt per rack we can able to load in our labs and data center. And next is on liquid coolings. Okay, so in this there are two types. One is direct to chip, or by using cold plates, so that is one type. So in this there are two. One is the single phase and two phase direct chip liquid cooling methods. So next is in new technology, liquid immerse cooling. Okay, so in this also there are two um, methods. One is a single phase and two phase liquid immerse cooling. With this new technology, so liquid immerse cooling technology, over 100 kilowatt per rack, so that much rack density we can able to load. Okay, so all these main three HVAC um, systems, okay, PAC, IRC, and liquid immersion cooling setup. So detailedly we are going to discuss. As I already told you, the little bit more on PAC because right now present overall most of our data center and labs are enriched with the PAC units. So that we discuss a little bit more. No case study in this video. So I'll be doing upcoming videos, the calculations, scenarios, and case studies I'll upload. So it is only the touch and base how PAC, Enro, and liquid coolings are supportive for data center to optimize energy consumption. Um, the question comes, why PAC? Okay, why not normal comfort cooling? Why PAC or indoor cooling or liquid immersion cooling for labs and data center to support IT hardwares? So this is because IT hardware produces unusual and concentrated load. Okay, it is not distributed across all the floor area or lab area. It is very concentrated within the rack. It produces heat loads. Okay, so we need to mitigate the AC load required by the particular rack area. And those servers and racks are very sensible for temperature and humidity. Any variation in temperature that can cause a tripping issue in servers, and in humidity changes that can severely damage the server itself. Okay, so that is why we should have the precise control over temperature and humidity, as well as we need additional airflow or additional capacity of airflow requirement to mitigate the heat load of labs and data center. So that is where our new HVAC concept, precision air conditioning, and IRC cooling and liquid immersion cooling are coming into pitch. So let's see what are the features precision air conditioning unit is having. So precision air conditioning unit are very reliable system that can operate round the clock, 24 bar 7, 365 days it can operate. And it has a precise control over temperature and humidity. We all know, like, humidity control, PAC is enriched with humidifier and dehumidifier with a set of heaters, so that have precise control over humidity, and it will give required humidity level at data center and lab area. And it can run continuously 24 bar 7. It is built to run that. uh, and it can manage high level sensible heat emitted concentrated load at server level. It will handle very easily. And it has got better air distribution. We can able to plan very air distribution equally, or concentrated load, hot as well, cold as well. We can able to easily distribute air through multiple PAC units, even though connected in parallel. And compared to um, normal comfort cooling. Okay, so PAC is higher airflow rates. Okay, usually the comfort cooling have 300 to 400 CFM per ton, the design, but PAC we can able to design up to 500 to 900 CFM per ton. So next is done for larger server loads. Multiple units can be synchronized together to automatically handle variable AC loads. So it has got static smart control. So as well as so unit to unit logic sequence can be built, like auto sequence changeover by standby. And so recommend based on the written area temperature, changing the actuators positions, and uh, fan flow speed can be controlled. And From PAC to PAC, the logic sequence and signal transferring can be easily made, unless comfort air cooling. So it is very easy to sync PAC, multiple PAC unit together to meet the required AC load by data center and lab. So another few points on most of our PS unit are bottom throw, because most of our lab or data center are raised floor, where we plan supply air bottom throw. And a PAC with top throw also available. Rarely we can see, but most of our PAC units are bottom throw supply. And next is on nowadays all PS units are coming with EC fan to optimize the energy consumption. And I already told it has got a static smart control system where based on the return air temperature, it will control fan speed and actuator positions. And as I already told, it can unless comfort cooling 400 to 300 to 400 CFM per ton, the design of PAC can go up to 500 to 900 CFM per ton. Let us see like types of precision air conditioning units. So we already discussed PAC with the chilled water, that usually we call it as a crack units. Computer room air conditioning unit supported by chilled water line through air cooled chiller or water cooled chiller or combination of both air cooled and water cooled chiller. So next is on DX units, direct expansion unit, whether the units are indoor units are placed nearest to lab and data center area, and outdoor units are located in balconies or nearest balcony or terrace area. And let us quickly see like what and all components direct expansion unit having. It is pretty much same as refrigerant cycle. It has got compressor, condenser, air dryer, expansion valve operator, and we already discussed that present PAC units are enriched with EC fans to optimize the energy consumption. So in upcoming video, I'll upload refrigerant cycle in detail explanation, as well as some cooling tower calculations and scenarios and case studies. So coming back to PAC, the third type of PAC is it's a combination of both chilled water and DX that we call the dual fueled. In this type of PAC unit, dual fueled, it has got two coils. One is supported by chilled water line, and another is refrigerant supported by outdoor unit. The logic sequence can be made in this, like the primary are the chilled water. Whenever the issue with the chilled water line, then unit is automatically moved to DX mode and vice versa. So it is give more redundancy for a lab and data center infrastructure. Next is on free cooling. So we have not see many PS unit which is operating at direct, I mean, a free cooling setup. Uh, One is on direct free cooling. So in this a kind of setup where 100% fresh air, okay, ambient air is pumped into data center, and the the return air from the data center is forcibly pumping out to atmosphere. Okay, so in this 100%, it is very energy optimized. Okay, it will reduce energy consumption, but pumping 100% ambient air to data center, it is always a risk. Um, Even though humidity controller we placed, so this always risks the critical infrastructure supported by 100% ambient air. To mitigate that, that indirect free cooling come into pitch. Indirect free cooling is nothing but mm, it's same ambient air pumping to the data center. Only part is through heat exchanger. Okay, so the portion of ambient air will be pumped into data center through heat exchanger. So the again the in indirect cooling also, it require the positioning of heat exchanger space and additional setup. Okay, so that's what the difficulties in direct free cooling and whenever matter comes to PAC with the free cooling. So that is why most of data center and lab infrastructure, they have PAC units, so not integrated with free cooling setups. Further to PAC HVAC setup discussion, what are all key challenges and solutions? Let us go through. Like one is on rack internal circulation, or short cycling. Also those part, because many of the lab and data center racks, it is not completely loaded. Okay, many of the area is kept empty where a short cycle will happen. That will consume more energy, and to optimize energy, so we need to add blanking panels in all racks wherever the slot is not utilized. to overcome short cycling challenges, we need to add uh, blanking panels. So next is on raised floor system, major contribution air leakage. So air leakage is pretty much a major issue through like the cut tiles or doors nearby door. Um, so those are really area major air leakage will happen. So that we need to close properly, and unwanted tiles cut has to be avoided. And if already there, we need to replace or we need to close that gap for air leakages. And the next is on air circulation. Okay, so improper supply air distribution. There is a always the below flooring in a lab and data center. There are two main component. One is on electrical cable tray that will pass below flooring, and second is on fire suppression systems. Okay, so that is also below flooring. There is a setup, so that will obstructs the supplier to distribute properly. So we need to make sure sufficient gap provided for airflow circulation to ensure proper air distribution. Okay, will happen, and we need to make sure that will not causing a issue of air distribution, especially on cable tray, power cable tray, and suppression systems located on below fall flooring. And the next is on hot to cold issues. So it is always like number of servers which are located. It is always different loading setup. One rack is consuming like 8 kilowatt, another is only 2 kilowatt, another is there's no load at all. It is empty panel. So that kind of distribution, uneven distribution in rack loads. So that we need to check, and we need to increase the CFM to the loaded racks and reduce the close the tiles by hard tiles wherever the load is less, or load is air distribution supply air is not required. We need to close by hard tiles. And if at all doing all the necessary action, if still we have a hotspot issue, then we can go for installation of booster fans for respective racks, which is having required more supply CFM compared to other racks. So we can go for booster fan installation as well. So next is a key point to be noted here is the power PDUs, power cables. It is always should be in a cold agile area, and a network cable, it always should be in a hot agile. Okay, usual setup of lab and data center, our power cable always comes in below flooring to the rack. Or else it will be on a cable tray or cable trench and above top. But the PDUs which is located, we need to ensure that those PDUs are located in cold agile area. So, and the network always on above, the racks. It will always in hot agile area. As I said earlier, there's no calculation or case study in this video. Okay, but the most important formulas for calculation of HVAC system effectiveness and airflow efficiency and cooling system efficiency, and how to calculate PUE. So those formula we touch base in this video, because those are very important cross check how exactly our HVAC system is delivering to respective like labs or data center. So let us quickly see the formulas pertaining to efficiency and effectiveness. So first is on HVAC effectiveness. So this is IT kilowatt divided by kilowatt HVAC. So the total IT load, the UPS load, which is feeding to lab and data center, so that is IT load. And pure HVAC load, which is connected to mitigate the heat load of those servers, so that is HV load in kilowatt. So if we IT load kilowatt divided by kilowatt consumed by HVAC system, that gives HVAC effectiveness. So it is the standards parameters for HVAC effectiveness is 0.7. It's a standard. Your HVAC system. If the ratio comes kilowatt by 80 kilowatt by HVAC kilowatt at 0.7, then your system is working on a standard level. And if it is comes to 1.4, it is in good condition. And the ratio comes 2.5, then your HVAC system is most optimizedly working, and thereby saving some energy. So to there's no case study in this video, but I have tabulated for your ready reference. Okay, so let's go through that table. So let's take one IT load, say 1 megawatt, 1000 kilowatt, and to mitigate 1000 kilowatt, so HVAC is consuming 1500 watt. Okay, then IT kilowatt by HVAC kilowatt 0.7. So that is the standard. Okay, so you're not in completely energy optimized. So you are within the standard limit. So if the ratio comes like a same 1 megawatt load, so 700 tonnage of AC is fulfilling. Okay, so then your ratio is 1.4. You are in good stage. And for better, like same 1 megawatt load, your HVAC cooling system consuming 400 watts. Okay, 400 kilowatts. Okay, then it is a very better. So all this PAC2 improvisation of enrocooling to liquid immersion, air to fluid, why the technology evolving happening to achieve from standard to good, from good to better. So that is why this technology is evolving. So as you can derive and calculate all our normal chilled water connected PAC and DX units. Okay, they are giving between standard to and good. So indoor cooling, it's bit good to better condition, and liquid immersion cooling will give better HVAC effectiveness. And the next is on airflow efficiency. So it is total fan power in watt or kilo in watts divided by total fan airflow in CFM. And the standard is to deliver a fan 1.25 watts per CFM. If the very good situation is working 0.75 watts per CFM. For better, it is 0.5 watts per CFM. So again, it is from industrial fan, from induction motors to the EC fan. Okay, so earlier if you cross check with the wattage and CFM delivery of induction motor, it is all lies in standard area. So now EC fans, it lies in good to better, because in PAC units again the gear losses are high, very high. So that is why in PAC units it's giving good. In indoor cooling, so it moves to better. Okay, so in indoor cooling, if you check watts per CFM, so obviously it will come around 0.4 or the 0.5, 0.6 watts per CFM design. But in PAC, so it is coming around some 0.75 to 1. And if you go for induction motor, it's obviously it is 1.25. For a quick, it is tabulated here. Let's say about two fans, 4.25 kilowatt into two, it's working. Total 8.5 kilowatt, 8,500 watts, delivering 6,800 CFM. Then watts per CFM lies is 1.25, that is standard. Standardly, it is delivering the same capacity of 8.5 kilowatt. If it is delivering 11,300 CFM, it's come 0.75. It's pretty much good working and delivering energy efficient one. If it is the same 8.5 kilowatt EC fans motor, okay, so it's delivering 16,200 CFM. It's better. It is energy is optimized, and if the same 8.5 kilowatt, if you required only 6,000, it can operate with only half of the speed. Okay, so and consume less energy. Okay, so that's what the standard good and better categories are in airflow efficiency. And next, see cooling system efficiency. So cooling system efficiency is average cooling system power in kilowatt and average cooling load in ton. It's simple IKW, kilowatt per ton. So let's see standards. So standards are 1.1 kilowatt per ton. It's a standard. All our air cooled chiller, its rating IKW is 1.1 to 1.2 kilowatt per tonnage, and a good lies between 0.75 kilowatt per ton, and a better lies between 0.5 kilowatt per ton. So all our water cooled chillers are built for 0.5 to 6, 0.6 kilowatt per tonnage. That is why water cooled chillers are more efficient than air cooled chiller because of less energy consumption. Water consumption is there, it's another part. Even if you can include the water consumption cost, so still it is efficiency wise it is better than air cooled chillers. So let's very quickly, let's take 100 kilowatt load. Okay, so for that 100 kilowatt load, so 90 tonnage of what the HVAC system consuming 100 kilowatt to deliver 90 tonnage, then the IKW is 1.1. So most of our air cooled chillers are, and HVAC system are consuming 100 tons same and delivering 133 tonnage of AC require requirement, that is 0.75. Then our HVAC systems are working in a good range, and if the same 100 kilowatt consuming and delivering 200 tonnage of cooling requirement, heat loads requirement it is delivering, then it is 0.5 kilowatt per tonnage. So that is a very better and good range, very energy optimized stage of cooling system efficiency. So let's very quickly see the power utilization factor. So power utilization factor is the total facility load in kilowatt divided by total IT load in kilowatt. So usually all our traditional PAC units with hot or cold containment, we can able to achieve between 1.5 to 2, like between average and efficient. So some of without containment, uncontained room conditions of labs and all, it is always more than 2. And with in-row cooling we can able to achieve again 1.5, 1.6, we can able to achieve efficient stage. And with the liquid immersion cooling, obviously we can able to achieve PUE 1.2 and below. The second HVAC system what we are discussing today is in-row cooling. So indoor cooling is a room cooling system is placed inline or parallel with server equipment. Okay, and air drawn through rear side of, I mean, return air side. It will suck and it will give cooled air to the cold asile where the front side of rack located. So it is a pictorial representation how indoor cooling setups are between the racks located. So it is like these are all two indoor cooling. Okay, these are two indoor coolings. Okay, which is located in between the racks. Okay, so it will suck the return air and it will give water supply air towards rack front end. Okay, and inside there is a coil and heat rejection will be happened through chilled water line, and this is a hot asile and this is a cold aisles. Okay, so it is located very near to rack, so that is why the airflow requirement compared to precision air condition located a little away from racks. Hence, the fan capacity requirement will be less, and the power consumption also very less compared to PAC units. So what are the advantages of this is typical how indoor coolings compact indoor cooling units, okay, available at market. So to place exact I mean in between rack parallelly, So one is on lower fan power consumption to deliver supply air. Yes, because it is very near to the rack, and air leakage. I mean, air losses are very less compared to PAC units, unless it is a bottom throw, more obstacles, more leakages. So it is pretty much less in indoor cooling. So that is why capacity of the fan also required very less, and higher set point. So we can able to set higher set point uh, in indoor cooling, because it is energy losses are very less compared to PS unit, since it's very near to rack. So that is why we can go for higher setting of PS unit, and supply air controlled. Less need of humidity control. Okay, so hence it is very near to rack. It is not far away. There's no obstacles. And higher set point where we can go for. Then obviously the humidifier will come into pitch very rarely, so usage of humidifier is always a energy consumption. Okay, so if less use of humidifier, then obviously it will increase the energy, I mean optimize the energy consumption. And a compact and modular design, and handled variable rack density, as we already discussed. Indoor cooling can able to uh, what load up to 40 kilowatt per rack, so that density of rack can be supported by indoor cooling. Now let us discuss on last type of HVAC setup, the modern new technology setup, liquid cooling types. Okay, so in liquid cooling types there are two types. One is on direct to chip using cold plates. Okay, and next is on liquid immersion coolings. Okay, so in direct to chip liquid cooling, cold plate types, there are two. One is single phase and two phase. And in liquid immersion also there are two types. One is on IT chassis, and next is on bath or open bath or tub type. So in this IT chassis also, it is a single phase method, and tub or open bath, it is both single phase and two phase are available. So one is on in direct chip method, we can remove up to 60 to 90% of server heat load via liquid. Here, the PAC, I mean, additional what the setup we are having, that is also required, because it is partially remove the heat load from the servers. So rest has to be taken care by the normal HVAC setup. Okay, so in this method, direct to chip, liquid is not directly physically contact with IT component. Okay, so it is only on the top of IT servers it's located, a cold plate it is located. But in liquid immersion cooling in bath, so we can able to extract more than 95% of heat rejected by servers. And in this type it is directly fluid or engineered electrofluid. It is direct contact with IT component. The IT components are immersed in this dielectric fluid. So let us go quickly on all this type, how it is working. Next is on direct to chip or cold plate. Okay, so in this technology, the direct to chip, the cold plates are located on top of the heat sink. Okay, the server PCB heat sinks, it is directly located to extract the heat generated by the board directly. Okay, so it is also having a single phase and two phase evaporation units. Okay, so in this cooling, main disadvantage is like it can extract 70 to 75% of the heat rejected by the equipment, IT hardware. But again, remaining 25 to 30% has to be taken care by um, our other HVAC system supported, like this PEC units or direct expansion unit, ES unit, whatever we installed, that needs to be taken care by additional cooling requirement. So it is a combination of both. If you go for direct chip cold plate implementation in data center or lab, so it will extract 70 to 75% of heat directly rejected by the server itself. Okay, so that definitely there will be energy optimization, energy saving will be there, cost will be reduced, operating cost will be reduced. But although we required some of 20 to 25 30% of heat rejected by server has to be taken care by our usual HVAC setup like PAC or duct expansion AC units. So the main component of a direct to chip or cold plate is cold plate and tubing, so to circulate the fluid, and a manifold and CDU unit, coolant and distribution unit. Let us quickly see how the cold direct to chip cold plate technology works through small video. There's a direct to chip liquid cooling solution, okay, where the cold plate are directly mounted on top of the heat sinks of all the PCB units or server boards, okay, where it will extract the heat rejected by the board directly. And in this cold plate, the refrigerant will be circulated through pumping system by through CDU, and the hot after rejection the fluid will be pumped back to the cooling system like chillers or outdoor units. Okay, again the cooling refrigerant will be pumped into cold plate, okay, through CD unit, through pumping mechanism. So like this direct to chip cold plate system works. This is a typical diagram how a direct to chip cold plate works. After circulating pump, cooling refrigerant will fluid will flow to the cold plate. So cold plate will extract the heat directly from the uh, servers boards. Okay, so that hot fluid will again circulate back to chilling chillers or cooling media, whatever the setup we have, and again the cooled fluid will be circulated back to the cold plate through CDU unit. So this is how this direct to chip or cold plate method will work. Next is on engineered fluid, liquid immersion cooling. Okay, we'll have engineered fluid or direct fluid. What is exactly this engineered fluid or direct dielectric fluid is? It is non-conductive over 60 kVA till 60 kVA. It is non-conductive, and over 5000 amps it can withstand. We can say like it is completely non-conductive. There's no conductivity in this fluid, and it is non-toxic as well as non-flammable, and it is biodegradable fluid, and it is lighter than water, and it is having very high viscosity compared to water, and it is very clean and environment friendly, and it is non-corrosive. Most important thing, the characteristics of engineered fluid or dielectric fluid is it has got a constant boiling temperature at 56 degree. If the temperature shoot of more than 56 degrees centigrade, then this engineered fluid will be vaporized. And again, when the temperature comes below 56 degree, again from vapor, it will convert back to liquid form. So this is the beauty of engineered fluid or dielectric fluid characteristics. Okay, let us quickly see one video where they are showing some demo of engineered fluid or dielectric fluid, how it works. Is powering engineer fluid, dielectric fluid directly to the server, okay, which is in on condition. Okay, so since it is a non-conductive, okay, it will not affect even a small moisture content that can cause a short circuit. Okay, but thing is, it is completely non-conductive, and it is corrosion flame non-flammable. It will not have zero impact on server in when it is in on condition. Even in this inside in this fluid, the our what server fans that will be in on condition. Okay, so that much useful fluid is that is called engineered fluid or dielectric fluid. So let us see the technique of liquid cooling, IT chassis. So in this, the ready-made IT chassis will come. So with uh, liquid immerse inside the dielectric fluid dipped chassis will come, where you need to just plug in inlet and outlet connection of fluid circulation. Okay, through CDU unit. So single phase immersive IT chassis dielectric fluid cool the equipment. So active pumping to liquid within the servers, okay, and heat to liquid flow through the heat exchanger water loop where it is cooled. There is a heat exchanger, okay, where this fluid will go again cool back, and it will come back to the server IT chassis, and the heat exchanger whatever mechanism to chilled water evaporator coil or now DX whatever the heat exchanger is there it will exchange the heat, it will become cold engineered fluid will flow back to IT chassis. It is nowadays it is ready-made available IT chassis. So like this IT chassis will come, it is all liquid immersion one. So there is a two um, opening will be there, you need to just plug in and out of fluid circulation to your heat exchanger CDU units. Okay, so this is one of the photo of IT chassis. It is completely immersed with liquid engineered fluid. Let us discuss on liquid immersion cooling single phase. We have seen the engineered fluid or a dielectric fluid, how effective it is. It is very non-conductive, non-toxic, and non-corrosive. By using that engineered fluid, how the technology evolved to optimize the energy, and how best that engineered fluid is utilized in liquid immersion cooling. Let us see. Let us go first by single phase. This is how the typical single phase liquid immersion cooling is, where the tank and inside the tank all our servers are immersed in engineered fluid. Okay, so and whenever the heat exchange will happen between extract happen engineer in between server to uh, uh, engineered fluid, so the hot engineered fluid will flow back to the heat exchanger unit which is placed. Okay, so there where our chilled water inlet and outlet, so the heat transfer will takes place between engineered fluid and uh, our chilled water line. So again the cooled engineered fluid will pump back to the server's tank, which is the tank which is servers are immersed in engineered fluid. This is how the cycle becomes. In this concept, multiple racks can be connected together to a common heat exchange unit, where the hot engineered fluid will coming to the heat exchanger, where heat extract will take place between engineered fluid and our chilled water line. Again, the cooled engineered fluid will be pumping back to uh, uh, our racks where our servers are immersed in engineered fluid. Let us very quickly see how liquid immersion cooling single phase works. So in this concept, the servers are uh, immersed in engineered fluid, and once the heat transfer will takes place from server to engineered fluid, hot engineered fluid will uh, flow to the heat exchanger unit, where heat exchange will takes place between engineered fluid and chilled water line, and hot chilled water will pumping back to chillers, and where the cooled engineered fluid will again pump back to the rack where our servers are immersed in engineered fluid. This is how liquid immersion cooling single phase works. It is the most effective method. This is the maximum level we can able to optimize energy, where the media is engineered fluid, not the air. Okay, so and it is straight away extracting the heat generated by the rack itself, so there is no losses in it. So maximum energy saving in this concept. Only part we need to mitigate operating challenges, like uh, the condition of heat exchanger, coil condition, water quality. So those part we need to take care for smooth operation. Any deviation in water quality or the or any contamination in the server liquid engineered fluid, okay, if that takes place, it is directly impacting to our servers. So those area risk we need to mitigate for smooth operation. But liquid immersion cooling is the best in terms of energy saving aspect. Now let us see the liquid immersion cooling two phase. Okay, so why it is calling two phase? Because here evaporation will happen. So earlier in single phase immersion cooling system, no evaporation. The engineered fluid will not evaporate. So once it reaches, it is always circulating in liquid form only through heat exchanger. It will cool and it will come back to rack, where heat exchange will happen between rack and engineered fluid. Hot engineered fluid again pumping back to heat exchanger. But in liquid immersion cooling two phase system, where servers are immersed in engineered fluid, and heat exchange will happen between engineered fluid and server. Once the engineered fluid got heated up above 56 degrees centigrade, it will evaporate, become vapor form. Okay, and that vapor, the condenser coil which is located here, supported by chilled water inlet and outlet. Okay, it is the evaporated engineered fluid will touch that, heat exchange will happen. When the engineered fluid temperature fall down to 56 degrees centigrade, again it will become a liquid form, again will drop to the same container. So both evaporation and condensation will take place within the tank. So that is why this is called two-phase liquid immersion cooling. Okay, let us see very quickly one video. Okay, how the two-phase liquid immersion cooling setup looks. So this is two-phase liquid immersion cooling setup, where servers are immersed in engineered fluid. Okay, so you can able to see it is not a it looks like water, it is not a water, it is an engineered fluid. Already we discussed is non-conductive up to 60 kVA, and up to 5000 ampere it can withstand. So directly heat transfer has been uh, whenever the heat uh, from the server, heat transferred to liquid engineered fluid whenever reaches to 56 degrees centigrade, it is evaporated. So after evaporation, it touches to the condenser coil, which is supported by chiller inlet and outlet. And once it is temperature reduced to 56 degrees centigrade, there condensation will happen. Again the engineered fluid will coming back to liquid form and pouring again in the same container. This is called two-phase liquid immersion cooling. Okay, so again, it is the best energy optimized solution for data center and the lab area. Okay, where directly heat will transfer to the liquid. Okay, not the air. Okay, we are not cooling usual tradition. Now PAC become a traditional method where air is used as a media to cool the racks. Here, the engineered fluid is used as a media to cool the server area, server racks. And the most important, it is directly cooling the hotspot of the what lab. Okay, so no comfort cooling required in that lab area. So it is most energy efficient compared to any another method. Let us quickly summarize what we have discussed today. One is on precision air conditioning unit with chilled water DX and dual fluid, and also we discussed about PAC with the free cooling systems. And In this tradition, currently PAC unit setup, lab and data center, it is very difficult to maintain the PAU because of various issues and challenges to maintain PAU. So we can able to maximum we can able to achieve like 1.8 to 2 PAU. So in in-row cooling, yes, we can able to achieve up to 1.5, 1.4, 1.6 up to we can able to achieve PAU. Uh, and In a liquid immersion cooling, we have discussed a direct to chip cold plate method. It is additional retrofit where we can reduce our energy consumption, adapting direct to chip cold plates to servers. And here also on the IT chassis, so readily chassis, if you go for servers rack with ready chassis available with immerse cooling, so that is also can reduce most of our energy consumptions. And next is on liquid immersion cooling. There are two types: single phase liquid immersion cooling, where only uh, condensation will happen through heat exchanger, no evaporation. If it is a two phase, both engineered fluid will evaporate, again it is cooled down, condensation will happen again, from evaporation to it will convert to liquid form. So that is why it is called a liquid immersion cool two phase system. Okay, so what is the use of liquid, air versus liquid? So first two methods are air as a media. Okay, so next to direct to chip and liquid immerse cooling, where dielectric fluid or engineered fluid as a media. So compared to air cooling systems, okay, so liquid cooling system are more effective because it is directly work or directly get the heat extraction from the server itself, rather than complete area cooling and server racks cooling. It is exactly spot the required cooling things of servers, and it will exchange the heat extraction from the server itself. That is why it is more effective, compared to more effective and energy saving compared to air cooling system like PEC and indoor cooling. So in this two phase and single phase system, up to 200 kilowatt per rack density we can build, and in two phase up to 250 kilowatt per rack we can able to install. And PUE, if we talk about in single phase, PUE can be achieved 1.02 to 1.03, and in two phase 1.01 to 1.02 PUE can be achieved in two phase liquid immersion cooling. So this is how where we exactly mitigate our energy consumption. Energy losses issue, and we can optimize our energy consumption to increase the rack density, as well as to optimize our energy consumption. And in liquid immersion cooling, the space requirement is also pretty much less. So in this we can able to easily tell, compared to air cooling system, so fluid cooling system are more effective and efficient for data center and the lab infrastructure. Thanks for watching this video. Hopefully this video is more informative and knowledge based. Request you to kindly subscribe and share with your friends and colleagues who is working in facility field, especially technical field. It may useful for them. Once again, thanks for watching this video. Please subscribe and share.